so much for the invitation to talk at this virtual symposium. I think it's a great initiative that you've started. Both me and my group have listened into both the previous ones, and we look forward to also Thomas' talk later today. So I will indeed be talking about VBX chemistry. I'll give you a very brief introduction and then go on to the synthesis of VBX and then the metal-free vinylations that we have developed using VBX. So here's a recent picture of my group. And I would just like to first tell you a little bit about what we do apart from VBX in the group. So we have focused quite a lot on synthesis development for iodine-3 reagents to make them easily available also for people who are not totally into hypervalent iodine chemistry. So we've been mainly looking into diaryl iodonium salts, but also alkynyl iodoniums, EBX, and now most recently VBX. We've also spent quite a lot of time on metal-free development of methodology for reactions with these reagents, especially diaryl iodonium salts. And the reason that we want to do that is that they are selective, reactive, and also seen as sustainable reagents. And when we can, we try to apply the methodology towards biologically active targets. So here's just a fast slide to show you the first methods that we did develop in my group. That was to make diaryl iodonium salts. And if you can see my pointer, you see the conditions. We use MCPBA and an acid, either triflic acid, tosic acid, or BF3 for a variety of synthetic methods that we have developed to make iodine-3 from iodine-1 in a fast and efficient way. So when we were done with diaryl iodoniums, we went on to look at the synthesis of alkynyl iodonium salts. And this work was developed quite early on by a postdoc, Ellie, in my group, starting with the idea that alkynyl iodonium salt had been known for very long. But again, to make them in an efficient way, starting from iodine-1 compounds was not developed. So we first found a method to do that straight with alkynes, but that had a very, very moderate scope. So then we went on to develop another method using boronic acid and boronic esters. And that method was quite general. And we then thought, can we extend that to make EBX reagents, since those have been very much used recently at that point by Wasser's group. And indeed, we could extend this methodology to make EBX reagents of various kinds. So taking an iodoarine, oxidizing that with MCPBA in the presence of tosic acid, and then adding the boron reagent, we would form the iodine-3 species in situ and then treat that with base to form the ring-closed Benziodoxolone. And that was possible to do with a range of aryl and alkyl change on the alkyl moiety. And we could also make those EBX reagents having silyl groups on there. So at that point, back in 2011, 2012, we started thinking about, what about vinyl Benziodoxolones? We looked into the literature and it turned out that they were almost unknown. So Kitamura published already in '96 that taking an EBX reagent and treating that with sodium azide, it was possible to form this heteroatom substituted VBX species. That has never been used in synthesis as far as we know. But over the time that we were developing this chemistry of VBX, there was a report by Wasser and co-workers where they found that taking an EBX reagent and treating that with a thiol, they could isolate a VBX, heteroatom or sulfur substituted VBX in low yields as an intermediate in their reaction towards alkynylation of thiols. So we then continued our work and we were able to, in the end, devise a one-pot synthetic method from iodine-1 to VBX reagents in a very similar way as we had been doing for the diaryl iodonium salts. We tried various boron derivatives and also silicon derivatives and found that boronic acids were the best for this type of methodology. We published this only in 2016 because we were struggling quite a lot with this synthesis, especially to get it reproducible. So in the end, we found a small scope where we could make VBX reagents with various aryl substituents on, both electron-rich and electron-withdrawing. However, coming to alkyl substituted VBX reagents, the yields dropped considerably. So that was a clear limitation to the method. So after we published in 2016, other groups have been involved in developing revised methods to VBX. So Nachtsheim's group was the first. They started from iodine 3 and took TMS triflate and again aryl boronic or vinyl boronic acids with an aryl substituent to form VBX reagents. And they found that to be more reliable than to go all the way from iodine 1. And now recently also Wasser and co-workers did a similar thing, starting from the acetoxy iodine 3 derivative, again boronic acids, and then they could form VBX reagents and also the derivatives with 2 CF3 substituents here at the X. So there are now plenty of methods to make VBX reagents, and even more so because you can also start from EBX and make heteroatom substituted VBX reagents. And the top reaction that I show here is from the group of Yoshikai. They were working completely in parallel with us and developed very, very nice methodology where they treated EBX derivatives with palladium catalysis and carboxylic acids. Oops, I don't know what happened now. Sorry about that. So then they got to these quite heavily substituted VBX reagents, and they've continued developing that type of chemistry since. And also Wasser and co-workers have developed a method where they make EBX reagents and then treat them under metal-free conditions to make various heteroatom substituted VBX reagents. So now there are plenty of ways to make VBX reagents with various substitution patterns, and that's really nice. So going on to what you can do with VBX reagents, I will go through a number of vinylation methods that we have developed. The first one is really quick. So in the original paper that we developed, when we developed the synthesis of VBX, we wanted to try the reactivity of the reagent. And we decided to use a comparison from the literature where Occhiai and co-workers had taken nitrocyclohexane to treat that with a base and then use this cyclic vinyl iodonium salt to get to these two products. So they got a mixture of the vinylated product and the arylated product, meaning that the chemoselectivity in this reaction was very poor. And we wanted to understand why it was so poor, and we wanted to compare that to VBX. So to make it a fair comparison, we synthesized an acyclic vinyl iodonium salt instead that would be more comparable to the VBX reagent that we had. And taking this substrate and treating it with this vinyl iodonium salt with the same base and same conditions as Occhiai, indeed, we did not see any arylation product. So that seems to be due to the cyclic nature of Occhiai's vinyl salt. But what we saw was instead a mixture of the internal alkene and the terminal alkene, where the internal alkene was the major product. With VBX, on the other hand, it was the terminal alkene that was the major product. So under the same conditions as Occhiai, we didn't get so high yield, but a clear preference of the terminal product. And when we did a mini optimization of the reaction and swapped solvent, we could increase this yield to 57% and a nice regioselectivity of the reaction. So we thought that this regioselectivity difference compared to iodonium salts was really interesting, and we wanted to go on investigating what VBX could do with other nucleophiles. So with that, I'll go on to show you a bit in more detail to other projects that we have developed, which is an S-Vinylation and a P-Vinylation. So when we were looking for various targets to try VBX on, we saw that again, Ochiai had done quite a lot of work on S-Vinylations. So you have two examples here. One where he's taking this thiol, already deprotonated, and treated that with this cyclic vinyl iodonium salt and got a nice yield of the vinylated product. Also, he showed with the more complex nucleophiles that he could get S-Vinylation, but you see here that he starts with an E-vinyl iodonium salt and he gets the Z product out of it. So that was also quite interesting. And then the final reason that we thought that going to thiol was a good nucleophile to try VBX on was that Wasser and co-workers had developed a very, very nice method where they could alkynylate thiols under very mild and metal-free conditions, as you see in this example. So during the time that we were working on the S-vinylation of thiols, 3 examples appeared in the literature where they'd taken a few examples, 1 or 2 examples in each paper, because the main focus in the papers were derivatization of EBX, but they used VBX to exemplify. So here's an example of a product that in the end is S-vinylated from a paper by Wasser. Here we see a more direct comparison where they actually take a thiol and they take this nice heteroatom functionalized VBX reagent and indeed get the S-vinylation product out of it. They go from completely stereoselective VBX reagent to a mixture of 7:1 in the product. And then there's one example by Miyake's group, also very recent, where they again were working with EBX, but then showed with VBX that they could do similar chemistry. So there are indeed examples that you could vinylate on thiols, but we wanted to develop the methodology to be stoichiometric rather than excess reagents, and also to have a good stereoselectivity. So when we took our VBX and started applying thiols to it, we didn't know anything about the regioisomeric outcome, although the examples I showed you in the last slide indicate what the outcome would be, but we didn't know when we started. But we did see a complete formation of the internal alkene, so opposite to what we saw with the carbon vinylation I showed you previously. And we got high selectivity for the E product. With the optimized conditions, we ended up with THF, butoxide, and room temperature. So very similar to our favorite conditions for arylations. We could, in the beginning, we saw a lot of byproduct formation from oxidation of sulfur that could be suppressed by using anhydrous degas THF. So looking into then, first of all, how the structure of VBX influenced the reaction outcome, we synthesized a number of core substituted VBX reagents. Substituents on the core of iodine-3 compounds have many times been shown to be influential of the outcome of the reaction. So we thought it'd be interesting to try both steric and electronic changes in the core. So here you see examples where we have the model compound without any substitutions, where we get a high yield and excellent EZ selectivity. If we put a nitro group in the para position to the iodine, we suddenly have arylation as our major product. So we get this type of product as the major. And the vinylated product was formed only in a small amount. With other substituents in the para position, we are back to seeing only vinylation, but in lower yields when it comes to the bromine substituent, and also decreased EZ ratio. Putting a methoxy substituent there, we get high EZ ratio again, but slightly lower yield. Going for ortho substituents, you see again a nitro group in the ortho position is really poor for chemoselectivity as well as yield. So again, the arylated product is the major one. And then if we put a methyl group in the ortho position, there are several papers showing that if you have a methyl or a methoxy substituent in the ortho position, you get a big difference in reactivity, but we did not see so much of that. So the yield was a bit lower and the selectivity was also a bit lower. We were also comparing with the acyclic vinyl iodonium salt. And you can see here that this behaves quite differently. So it only gave a 20% yield of the vinylated product, which was a 1-to-1 mixture of the E and Z isomer. So at this point, we were rather disappointed, thinking that none of these reagents that we had synthesized actually made it better. So then Esther went back into the lab and designed another VBX reagent. And it turned out that putting a methyl group in the para and meta position to the iodine did have a positive influence. So we got an increased yield and kept the really high diastereoselectivity. So we call this reagent our dimethyl VBX reagent now. So we found this result with the dimethyl VBX rather late in the project, and it is more expensive to synthesize. So for the general scope, we did use the parent VBX without any substituents in the core. I'll come back to the dimethyl VBX in a minute. So looking at the thiol scope then, if we start by varying the thiol and keeping the vinyl moiety intact, then you see that we have the normal possibility to change the aryl group of the thiol to include electron-rich, halide substituted. We could also have diortho substituted, so sterically hindered thiols, even though the temperature had to be increased to allow that. We could also vinylate aliphatic thiols, also with sterical hindrance, such as a terbutyl group. And we had examples where we did a divinylation of a dithiol, and that worked out really nicely. Going on to look at more functional group tolerance, we went for more sophisticated thiols. And you see here that both an allyl moiety, a furanyl, a pyridyl moiety was fine. Although, again, the EZ ratio dropped in this case. We could also have unprotected functional groups, such as amino and hydroxyl moieties in the substrate without having any interference. And here are more complex substrates, so the cysteine ester, and also this thiol that we have vinylated is captopril, which is an ACE inhibitor. So we thought it'd be of interest to see if we could derivatize that in the presence of a free carboxylic acid, and that worked out. And we could also vinylate this carbohydrate substrate. So looking in then to the VBX scope, what we could vary in this moiety, we could use different aryl substituents. You see here that the EZ starts to vary a bit. So when we have a methoxy substituent, the EZ is only moderate. We could have halide substituents and also electron withdrawing substituents in that position. Then, of course, we were really interested in trying out the beta heteroatom VBX reagents that had been published by other groups. So we synthesized those that Wasser had published and tried. And we had this type of reagent where X was either a nitrogen or an oxygen, and could use that to form these two products in really high yield, where we have formed then a tri-substituted alkene, heavily functionalized in excellent yield, and also high EZ ratios. So then going for di-substituted with another heteroatom, we tried with this reagent, but could only get the product in rather moderate yields. So then we went back and tried our dimethyl VBX instead. And it turned out that that reagent was much better for this reaction. So we could then isolate this highly functionalized alkene in good yields and again excellent stereoselectivity. So at this point, we were quite interested in using this dimethyl VBX core. So we tried this on a few normal vinylations. So where we had the model phenyl substituted vinyl group on that core. And it turned out that those vinylations were also very high yielding and gave high EZ selectivity. So our conclusion from this is that the model VBX works fine for most substrate, but if there's a problem, it can really be worthwhile to synthesize the dimethyl VBX instead. We tried also mercaptothiazoles as substrates, as you see here. We had to increase the temperature, but it was also possible to vinylate on those, as you see there. And we could also take a TMS protected thiol and deprotect that with TBAF in situ, and then treat that with VBX and get a good deal of the vinylated thiol in this fashion too. So we think that could be a nice alternative for more complex substrates that you want to keep them protected until it's time to do the VBX reaction. Okay, so with that, I'll go over to the P-Vinylation chemistry. So we were looking into the literature about functionalization of phosphorus nucleophiles with iodine-3 reagents. And again, there was a paper by Wasser's group where they had used EBX to form these alkynylated species, and they could do that with a variety of phosphorus nucleophiles. There was also one example on H-phosphonates where they took a vinyl iodonium salt and copper catalysis to form this internal alkene here. So we then started developing P-vinylations, and again, we were wondering which regioisomer will we get? Will it be the terminal alkene or the internal alkenes? And if so, will it be a diastereomeric mixture or not? So it turns out that with the phosphorus nucleophiles, we get the terminal alkene again, so completely different from the thiol nucleophiles. And the optimized conditions that we got were very similar to those developed by Wasser for the alkynylation of phosphorus nucleophiles. So THF, dBu, and room temperature. And we could alternatively also use BTMG in this reaction. And we saw a clear concentration effect. So the yield was much higher when we lowered the concentration of the reaction. So looking into the scope, this chemistry was developed by Adam and Laura. And if we start by looking into symmetric diaryl phosphine oxides, they could be vinylated quite easily. You see excellent yields. We could also put on spherical hindrance in the ortho position, so this dimethyl substituted substrate worked out fine, as well as this naphthol substrate. We could put on electronic donation and also fluoride substituents, whereas when we put on a CF3 functional group, the reactivity went down considerably, and we could only isolate 27% after heating for prolonged time. We could also try unsymmetric substrates, so having two different aryl groups on the phosphorus, and they worked out fine as well. Again, we looked into the VBX scope, and we could see that we could again put different functional groups on the aryl moiety on VBX. We could, in this case, use alkyl VBX reagents. We were not able to do that with the thiols, but they work fine with the phosphorus. And here's a quite nice example that would be rather sensitive to other we could also vary the substituent quite a lot here. You see, we now, in order to get these types of reactions to go, we had to go up in temperature to 60 degrees instead of room temperature. But we got nice yields also with allylic systems as well as benzylic systems. And we could also use normal alkyl substituents, again, with steric hindrance tolerated. The limiting case was to have a dialkyl phosphine oxide that was very poorly reactive. And going over then to H-phosphonates, again, we had to increase the temperature and now also increase the reaction time to get those reactions to go. But then we were able to develop a small scope with such substrates, and it turned out that this was a bit substrate dependent, whether it was DBU or BTMG, that was the best base. So you see a selection of H-phosphonates here that we could successfully vinylate, and also some more complex phosphonate substrates down here. And again, the limiting case was over here. When we have two oxygen substituents, we no longer could isolate the product very well. So the phosphonates were out of our scope. So to summarize, I've shown you that VBX is a novel vinylation reagent, that there are several methods to synthesize it. So you can either go from iodine 1 or from various iodine 3 reagents to form all kinds of VBX reagents. I also showed you this core substituted dimethyl VBX, which works really nicely in some cases. And also the vinylations of sulfur nucleophiles, phosphorus nucleophiles, and carbon nucleophiles. And at present, we're looking into the mechanism to try to find a general model to explain the reactivity and the regiochemistry with different nucleophiles. So that's work under progress. So with that, I would just like to show you this book, the Patai book, that was published last year, that has 20 chapters on hypervalent iodine, 1 chapter on hypervalent bromine, and you can buy those chapters individually online as well. So I really recommend that book if you want to read up more about hypervalent iodine. And with that, I would like to thank my group. You see the VBX team over here. It's been Adam, who was an exchange student from Poland, who was in my group for a couple of months. It's been Laura, a postdoc who was in the group for 2 years, who developed a lot of the chemistry, and Esther, who's a PhD student in my group who's been part of these projects and who's also doing the mechanistic studies right now. And you see the funding down here. So with that, I would like to thank you for listening, and I'm happy to take any questions.
Thank you for a wonderful presentation, Professor. We do have a few questions here. I'll ask them in order that they were asked. The first person asked, on slide 15, was there any rationalization concerning the internal versus the terminal olefination for the VBX versus vinyl iodonium salt?
Not yet. We decided to wait with trying to rationalize all of this until we had a couple of examples with different nucleophiles. And this is where we are right now. So that's Esther is now doing both calculations and experimental studies, so labeling studies, to try to understand the mechanism with these various nucleophiles and try to come up with a good explanation.
Interesting. Okay. Another one asked, why does the nitro substitution prefer aerolation for thiols?
So there's always going to be a competition which group that is favored, and we've been looking into this quite a lot when it comes to diaryl iodonium salts, and then the electronic effects are really strong. So the most electron deficient ligand will be transferred. So a diaryl iodonium with a nitrophenyl versus a phenyl, you'll always transfer the nitrophenyl group. When it comes to vinyl iodoniums and alkynyl iodoniums, usually the selectivity is always favoring transferring the vinyl or the alkynyl moiety. But it seems like when you put enough electron withdrawing substituents on the aryl moiety, then that selectivity takes over. So there's always a competition with these iodine 3.
Right. We have another question from Professor Wengernick. She asked, did you examine changing the nature of the cyclic tether, the carboxylate, and what effects does this have on chemoselectivity, stability, and reactivity? Ethers, sulfonate, covalent versus coordinative binding.
We've looked a little bit into the tether. I can't say we've done it very much. So we looked into, let's see if I can find the other. So this type of reagents where X is 2CF3 groups, we tried a little bit, but we saw lower reactivity than with the standard VBX, but we have not done any optimizations on that yet. So I would say it's way too early to say that that structure should be worse. I just think that those reagents need to have their individual optimizations, and we'll certainly start looking into more of those factors as well.
Interesting. I have one more maybe for you. For the dimethyl, the dimethyl VBX reagent that you synthesize, why would that one, or why do you think that one might work better, and how did you come up with, was it just a random screen of putting on different groups that you came up with that those positions, or was there some rationalization?
Well, I need to give the credit to Esther completely for finding that VBX reagent. We were looking into electronics and sterics, kind of following what was published before, and then it was mainly seen that any substituent in the ortho substituent could have a dramatic effect on the reactivity. So we were quite unhappy to see that the substituents that we tried did not really work. We were unable to synthesize some of the substituents that we were intending to put in the ortho position. But when we examine the results from this study, we see that the paramethoxy gives a nice reactivity still. And whereas if we go to less electron donating substituents or really electron withdrawing, we see lower EZ and also then going over to arylation. So we started thinking about other electron donating substituents that we could try. And you see the orthomethyl is not so great either, but it's reacting. And then Esther was able to synthesize this dimethyl substrate, but it was very late in the project. So most of the scope was actually done already when we found that this dimethyl VBX was so good. So that's always the way it is, isn't it? We were struggling with those heteroatom substituted VBXs and couldn't get any good reactivity with them. And that's when she found this VBX, the dimethyl VBX.
Okay, interesting. All right, lots of questions, but maybe I'll just ask one more if you if you would entertain it. Somebody has asked, what about for same reagent? What about replacing it with the methoxy groups instead of the methyls? Is that something you've looked at more? I guess more electron donating at those positions.
We have not done that yet. There's so many things left to investigate with VBX. So yes, I think there's no reason to believe that 2 methyl groups is the absolutely best ever. So that should certainly be screened.